for section 1 of chapter 2 of geometry. Your objectives in this section are to recognize the hypothesis and conclusion of conditional statements, state the converse of said statements, use counterexamples, and understand the meaning of if and only if. So to start out with, we have these conditional statements. Typically they are if-then statements made up of two different parts. You have your hypothesis, which usually follows the if. And would be considered your independent variable if we were in a science class right now. And then you have your conclusion that usually follows the then part of your statement, and that would be your dependent variable in your science class. So yeah, there's a little bit of overlap here, but math is the language of science, right? In that form, again, just to make that even more clear, we're going to talk about how we have, didn't mean to make that extra mark. If P, then Q, right? I'm going to use P for my hypothesis and then Q for the conclusion on the next slide. So you kind of need to have that labeled. So your general form for your conditional statements, right? There's actually a lot of different ways that you can see these. Yeah, I like to say if P then Q, but that doesn't mean that that's the only way that this could work. It could just be Q if P. I could have P implies Q. I could have P only if Q, right? If you have that only if, it is always followed by the conclusion. So these are our general forms for those conditional statements. If I want to write a converse statement, I just flip it. If it was normally if P then Q, now it's if Q then P. Again, you can actually define that. The statement turned around. So normally if P then Q, now we got if Q then P. Counterexamples. And these contradict the conclusion, but keeps the given true. Excuse me. So we'll show you some example of those soon enough. Otherwise, IFF means if and only if. Biconditional, when both the statement and converse are true, they can be considered, they can be combined into one sentence using if and only if. Right? By rule, all definitions are biconditional. So every definition we've had before now, they're always going to be biconditional. So when we get to examples here, right? So I'm going to go through a couple of these. I'll do one, then you do one, right? Kind of like that. You just need to pause the video if you want to work ahead and then check yourself, right? Go ahead and hit play and check yourself when it's all said and done. But in these statements, you're supposed to circle the hypothesis and then underline the conclusion of each statement. So again, I'll do one for you, and then you kind of take care of the other three in this case, right? If today is Thursday, then tomorrow is Friday, right? My hypothesis would be today is Thursday because that follows my if. Then is usually followed by my conclusion. So tomorrow is Friday is my conclusion in this case, right? Again, if you want to pause, try and do the next few yourself. Now's a good time to do that, but I'm going to go through the answers for each. A number is divisible by 3 if it is divisible by 6. Again, the if is usually followed by your hypothesis. So if your number is divisible by 6, then it's probably divisible by 3, right? A person can run for the Senate only if they are 30 years or older, right? If I say only if, that's always followed by my conclusion. So I need to underline that part, and then you can run for the Senate is my hypothesis, right? AB is congruent to CD. Line AB is congruent to segment CD. That implies that the length of AB is equal to the length of CD. Circle my hypothesis, underline my conclusion. Converse statements, right? All I'm doing is flipping this around, right? If it starts out as if it is raining, then the ground will be wet. The only thing I'd have to do to change it is say if the ground is wet, then it's raining, right? If x plus 3 equals 12, then x equals 9. Right? If I want to flip that, I just say if x equals 9, then x plus 3 equals 12. Again, the idea is that we can compare before and after. If it is raining, then the ground will be wet. That's always true, right? Unless you happen to be under an awning, right? That could change things. But if it's raining, the ground will generally be wet. But if the ground is wet, does that always mean that it's raining, right? So I could have a fire hydrant that's just been opened up recently. So that's not always necessarily true. Whereas if something is biconditional, both things would be true, both the original statement and the converse, right? If x plus 3 equals 12, then x equals 9. If x equals 9, then x plus 3 equals 12. Either way, that would be true. So I'm just writing converse. I'm just flipping the statement. It should be simple enough. Counterexamples, right? This is where I might have to come up with a different example for that conclusion. So just because it has 4 legs doesn't mean it has to be a cow. That cow could also be a dog. It could be a cat. It could be a rat. It could be a lot of different things, right? So lots of things have 4 legs. Not all 4-legged things are cows. You could have a lot of different examples. So providing counterexamples is just proving that statement wrong. Because just because Bill lives in Nebraska doesn't mean he has to live in Lincoln. He might also live in Gordon, or he might live in Clinton, or he might live in Rushville. Lots of options there, right? So counterexamples, not too tough. Rewrite the pair of conditionals as biconditionals. Again, if both the statement and converse are true, then you should be able to write both of these statements as a biconditional. So all I would have to do is just say, okay, if it's a right angle, it is a right angle if and only if the measure is exactly 90. Right? I could flip that. I could say if the measure is 90 degrees, then it's a right angle. But again, if I say that if and only if, that implies that the flip is always true, right? And that's what I meant before when I said all definitions are biconditional. By definition, a right angle is 90 degrees. So if I have a 90 degree angle, then it has to be a right angle. So conditionals and their converse can both be true, but then they are biconditional. All right, so that's all you need in your notes. And just go on to the worksheet for today.